Welcome to section 9.4, where we're going to discuss special right triangles. Two things we should be able to do at the end of this video. One, find the side lengths of special right triangles, and two, use special right triangles to solve real-life problems. For goal number one, we're just going to talk about the two different types of special right triangles that we have. One is the 45-45-90 right triangle, and the other is the 30-60-90 right triangle. Now again, I want to focus on the fact that we're talking strictly about right triangles. So the 45-45-90 is simply the right triangle where both angles, or both of your acute angles, are 45 degrees. And the 30-60-90, then it would make sense that one of the angles is 60 degrees and one of the other acute angles is 30 degrees, and of course we have our right angle given. Now, they're not always going to be shown as given. We might have them, switched around. It might be upside down or something like that, but we should be able to identify them by their angle measurements. This slide here has all of our critical information about special right triangles. So what you want to do is press pause here in a second and copy all of this into your notes. Make sure that you label the first one 45-45-90, and make sure that you get this diagram into your notes. Then, the second piece, label it 30-60-90, and make sure that you get this diagram into your notes. It's not so important that you get all of the wording here, but mostly the label and the picture with all of the blue notation. So press pause now, copy that into your notes. Goal 1 is to find side lengths. In example number 1, the first side length we're looking for is the length of this hypotenuse. We have the other sides given as 3 and 3. Now I know it's the hypotenuse because it's directly across from the right angle. That's always the hypotenuse, as we've learned in earlier sections this year. I've taken the liberty to bring a copy along from the other slide onto this slide. Now, instead of labeling the sides, x, x, and radical 2x, I've labeled them with k's because our example at this moment uses x. So I'm just going to shrink this down and sort of slide it right up next to our example. I know from looking at my model that the hypotenuse is equal to radical 2 times a leg, or radical 2 times k. So what I'm going to do is simply say that x is equal to radical 2 times k. But I know from the given in my example that k has a value of 3. So x is equal to radical 2 times 3. And the only thing we don't like is the way we have that written, or at least the order in which it is written. So x is equal to 3 radical 2. And that's all we can do, unless we'd like to change it to a decimal, which we don't want to do. Continuing to work on goal 1, we're still looking for lengths of sides. This time, we're looking for the length of one of the legs, and we've been given the length of the hypotenuse. And so all I'm going to do is associate the length of the hypotenuse with something on the actual model that we started with. So, radical 2k is the hypotenuse in our model, and the value of the hypotenuse in our example is 5. Now I just need to solve for k. Once I have the value of k, that's equivalent to the value of x. So I'm going to divide by radical 2 on both sides. And k is simply equal to 5 over radical 2. Sometimes this answer is sufficient, but we don't care to have irrational answers, which means we don't like this radical 2 in the denominator. So what we're going to do is rationalize the denominator, and we're going to multiply by the conjugate on top and bottom, which is radical 2. The reason why we do this is, as a result, we get 5 radical 2 on the top, all over radical 2 times radical 2 is radical 4, which turns into 2 on the bottom, and 2 is a rational answer, so we've rationalized the denominator. On the top, we're going to have 5 radical 2. At this point, if you get to this part, I'm pretty happy. If you can get all the way here, that's even better, but that's going to take a little bit of practice. Finding the value of x, the basic unit in your model, is really the key to the whole show. So in this particular example, we have a given value of 5, and then we're looking for the length of the hypotenuse and the length of the short side. Now when you match these things up, s is equivalent to the length of x. So as soon as we find x, we found the length of s. Afterwards, the hypotenuse is twice x. So in order to find the value of t, we'll need to multiply the value of x times 2. So first we need to work on finding that value of x. So we associate a portion of our model to a given value. I can associate radical 3 times x is equal to the value of 5 in our example. So we're going to divide by radical 3, divide by radical 3, and we get x is equal to 5 over radical 3. Now at this point, I would say, well, s is equal to the value of 5 radical 3, and t is twice that value. But again, let's try to rationalize that denominator. This time, our conjugate is going to be radical 3, and we're going to get a value of 5 radical 3 all over radical 9, which is x equals 5 radical 3 all over 3. So s then is equal to that very value, 5 radical 3 over 3. T is going to be equal to twice 5 radical 3 all over 3. So t then is worth 10 radical 3 all over 3. As we move on to goal number 2, we're going to use this newfound knowledge to solve real-world examples. We start with this concept of a tipping platform, which is used to take a large truck and actually lift it in the air and dump the contents of what's in here out onto the ground, or into a bin, or whatever. So we have a tipping platform as a ramp used to unload trucks, as shown on page 551. How high is the end of the 80-foot ramp? So this is what we're looking for, the length of this side, when it is tipped at a 30-degree angle. So we want to draw our model. And as we draw our model, keep in mind that this is where the 30-degree angle is. And this original ramp is now this part. So this is our 80-foot piece. It is our hypotenuse. Over here is our 60-degree angle. And I want to associate these parts with our original model. So this is 2x, this is x, and this is radical 3 times x. So what I'm going to use now is this piece right here. I have a given length of 80, and I know that in the model 80 is worth 2 times x. So I'm going to use that to solve for x. Simply going to say 2x is equal to 80, so x is equal to 40. If what I want to know is how high this thing is in the air, it's x feet in the air, and x is equal to 40, so our answer is simply x is equal to 40 feet. If you notice, though, the question moves on from there and asks, well, what about a 45-degree angle? So what we'll do is we'll just change our focus here and redraw another triangle. This is now a 45, 45 right triangle. Our ramp length is still equal to 80 feet. So what we should do is just kind of shrink this down and give us a little bit more working space. And we're going to solve for x. So radical 2 x is equal to 80. So x is equal to 80 divided by radical 2. Now, this is the one time where we'll start to say it's okay to use decimals to approximate. So x is approximately 56.6 feet. So the height of the ramp at this moment is approximately 56.6 feet. It might be interesting to add that the larger this opening angle becomes, the steeper the ramp, the higher off the ground it was. Originally we had an answer of 40 feet for this height when this angle was 30 degrees, and then as we enlarge that angle, this goes higher in the air. Seems to make sense. When you get back into class, you're going to work on some book problems from page 554. And at the very beginning, it's going to ask you to decide whether something is true or false. This isn't a 50-50 guess. This is just something that we're going to use our diagram to iron out. I'll do number 3 with you. So 3 asks, is the value of t 7 radical 3? Well, I guess I need a model that goes along with this. And I happen to have the model right here. So I'm just going to shrink that down, slide it up in here, and take a look. Well, who is t? T is the equivalent of radical 3 times x. Now, in our model given, I can see that x is worth 7. So t is equal to radical 3 times 7, although we would prefer to write it with the rational number first. So 7 times radical 3 is equal to t. Is this the same as this? Yes. So number 3 is true. And what you want to do is try to continue to associate the other examples like that to your original model and decide whether or not the arithmetic matches the answer shown. As you move on to other examples, again, the trick is always to match the unknown to a piece on your generic model. So for, say, number 10, if I want to solve for the value of a, I need to associate a with something on my model. I know that a in my problem is associated with the value of x in my real model. Now, I see that I have the value of 4 given, and I know that 4 is worth 2x on the model. So the value of x then is equal to 2. If the value of x is equal to 2, then I guess a is equal to 2. I'm going to box that up as a final answer. Now b in the model is associated with radical 3 times x. And again, I know that the value of x is 2, so b is equal to radical 3 times 2. But as you guessed, we don't like that order. We would prefer to write 2 radical 3, or 2 times radical 3. And we're done. One last example for me, number 11. Again, I can't stress enough, the faster you decide what x is worth, the faster you can tell me what any side length is worth. So in our model, we're looking for values of the legs, h and k. What's been given to me is the hypotenuse, and I know in my model that the hypotenuse of a 45-45 right triangle is radical 2 times x. And my given radical 2 times x is worth 9. So x is equal to 9 divided by radical 2. We don't like the denominator as an irrational number, so we're going to rationalize it by multiplying by the conjugate. So I get x is equal to 9 radical 2 all over radical 4. X is equal to 9 radical 2 all over 2. Now, h is worth x, and so is k. Both of these legs in 45-45 right triangle, of course it's an isosceles right triangle, so both of those legs are worth the same value. So h is equal to k is equal to the value of x, which is 9 radical 2 all over 2. I think you're ready to try some problems on your own.